Hello there, and welcome to the Sleepy Science Channel. I'm really glad you drifted your way here tonight. Maybe today stretched you thin, or maybe your thoughts have been running like an engine that refuses to shut off. Perhaps you've tried counting sheep and lost track somewhere, or perhaps you're the kind of soul who prefers drifting into sleep with cosmic ideas humming softly in the background. However you arrived here, you've reached a place where nothing is required of you now. You can let your mind loosen its grip. Let your breathing settle. Let your shoulders drop as if gravity has grown gentle for a moment. Tonight, you and I are going on a slow, calm journey into our home galaxy, the Milky Way. The Milky Way has been turning in the darkness of space for more than 13 billion years. A vast, spiraling structure of stars, gas, dust, and dark matter gently rotating, glowing from within. From a great distance, it might look like an elegant swirl of light painted onto the night. But when you move closer, closer than any spacecraft has ever traveled, its true nature becomes more complicated and far more beautiful. The Milky Way is not a smooth pinwheel. It is textured, layered, scarred, and alive with processes that operate across unimaginable spans of time. Tonight, in this calm and quiet moment, we will explore those structures and stories, slowly, peacefully, almost dreamily, letting them ease your mind toward rest. So take one more deep breath, letting it fill your chest, and release it softly. You don't have to remember everything you hear. You don't have to follow every detail. Just let the words wash over you like distant starlight. We begin with something surprising. The Milky Way is a galaxy built from the remains of other galaxies. For billions of years, smaller companions drifted too close, fell under its gravitational pull, and were gently but relentlessly pulled apart. Their stars were stretched into long, thin streams, tidal ribbons that wrap around the galaxy like faint trails of memory. One such galaxy, the Sagittarius dwarf, is being unspooled right now. As it orbits, its stars are peeled away, folded into the Milky Way's halo and outer disk. If you could look at the galaxy with perfect eyes, you would see these soft arcs of light looping across the sky, like whispers of long-forgotten collisions. And far away, another companion waits, the Andromeda Galaxy. Beneath the dark sky, on a clear night, you can almost see it as a tiny smudge in the constellation Andromeda. It looks modest, insignificant, but that blur is a vast spiral galaxy, roughly the size of the Milky Way, and it is moving toward us. Slowly, steadily, silently, Andromeda approaches. In about 4.5 billion years, the two will merge. Not in a violent explosion of stars crashing into stars, that almost never happens, but in a graceful, drawn-out dance. Their shapes will stretch, twist, and unravel. Spiral arms will distort into long curves. Tidal tails will sweep through space. And after billions of years, a new galaxy will emerge, larger and more rounded, forged from the combined stars of two mighty spirals. Even galaxies experience change, transformation, and rebirth. Some stars in the Milky Way are older than the galaxy itself. When we talk about stars, we imagine them forming inside the arms of the spiral, glowing gently in well-ordered orbits. But not every star in the Milky Way was born here. In the halo, a faint, spherical region surrounding the disk, astronomers have found stars so ancient that they likely formed before the Milky Way had settled into its current shape. These metal-poor stars contain almost none of the heavy elements created by later generations of supernovae. Their atmospheres are almost pure hydrogen and helium, the first ingredients the universe ever had. They are relics of a time shortly after the Big Bang, when the first tiny galaxies flickered into existence. Over time, those primitive galaxies collided and merged, and the stars inside them were absorbed into the growing Milky Way. Today, these stars drift quietly on long, inclined orbits, like elderly wanderers who remember a universe that no longer exists. Our own solar system is racing around the center of the Milky Way at a speed that is almost impossible to imagine, more than 828,000 kilometers per hour. Yet even at this staggering pace, a single orbit of the galaxy takes roughly 225 to 250 million years. That span of time is called a galactic year, and since the solar system formed 4.6 billion years ago, it has completed fewer than 25 of these enormous loops. When the first dinosaurs walked on Earth, our solar system was in a completely different region of the galaxy. Constellations wouldn't have looked the same. The sky held different neighbors. Everything in the Milky Way is in slow, constant motion, stars migrating, clouds drifting, clusters forming and dissolving over millions and billions of years. Even now, as you lie here listening, the Earth is turning. The moon is circling. The solar system is gliding along its orbit. You are part of this vast choreography, an unbroken chain of motion that continues whether you notice it or not. Although the Milky Way is ancient, it is not finished growing. It continues to pull in wisps of gas from the intergalactic medium. It captures stars from small dwarf galaxies. Streams of dark matter drift inward, adding to the hidden halo that surrounds everything we see. Sometimes this growth is gentle, thin clouds of hydrogen quietly falling into the disk. Other times, it is disruptive, satellite galaxies being torn apart, their stars scattered through the halo and disk. The Milky Way you see today is not the Milky Way that existed 100 million years ago or 500 million years ago. And the galaxy that will exist billions of years from now will be larger still, shaped by encounters and infalls that have not yet happened. Even counting the Milky Way's spiral arms is a challenge. You might think it would be simple to answer the question, how many arms does our galaxy have? But we are inside the disk, buried among billions of stars, with thick patches of dust blocking our view. For decades, astronomers debated whether the Milky Way had two arms for arms or something more complex. More recent observations suggest that the arms may not be continuous at all. Some may branch or fade. Some may be stronger or weaker depending on wavelength. The Milky Way may not be a perfect pinwheel. It may be a pliable, shifting structure shaped by star formation, gas flow, and ancient collisions. And within this swirl of arms, there are rogue stars, solitary suns traveling at incredible speeds. These hypervelocity stars are launched by dramatic gravitational events, often involving the supermassive black hole at the galaxy's center. Imagine a pair of stars orbiting each other passing near the black hole. One is captured. The other is flung away at 1,000,000 kilometers per hour, racing toward the edge of the galaxy and beyond. These runaway stars are rare, but they are real, and they remind us that even in a galaxy held together by gravity, there are moments of violent release. As we drift deeper into the galaxy tonight, imagine yourself floating weightlessly between the stars, carried along by a soft current of cosmic dust. There's no sound here, only the quiet brightness of starlight, the faint glow of nebulae, and the gentle pulse of invisible forces. The Milky Way stretches around you like a vast, luminous ocean. And just like an ocean, it has layers. Beneath the surface of the bright disk lies a thick and thin structure, each shaped by billions of years of history. The thin disk is where our sun resides, a crowded plain of young and middle-aged stars, rich clouds of hydrogen, dust lanes, and star-forming nebulae. Here, stars orbit the galactic center in relatively organized paths, weaving patterns that define the familiar spiral structure. But above and below the thin disk lies the thick disk, an older and more diffuse region. The stars in the thick disk tend to have fewer heavy elements, and their orbits are more energetic and inclined, hinting at a past in which the galaxy endured mergers, collisions, and internal instabilities. When you look at the Milky Way's disk edge-on, you don't see a flat line. Instead, you see something that bends, ripples, and warps, a gentle wave stretching thousands of light years across. This warp was almost invisible until astronomers mapped the hydrogen gas extending far beyond the visible stars. Something, perhaps the gravitational tug of the Magellanic Clouds or clumps of dark matter, has pulled part of the disk upward and pushed another part downward. Over millions of years, the warp rotates, like a slow, cosmic wobble that keeps the galaxy from ever being perfectly still. The idea of stillness hardly applies to galaxies. Even the space between stars, which looks empty, is not empty at all. The interstellar medium is filled with gas and dust, cold clouds, warm plasma, and hot bubbles formed by ancient supernova explosions. These pockets of gas weave around each other in filaments and cavities. They stretch, collapse, and tangle like strands of smoke drifting through a quiet room. Some regions are calm and thin, others are turbulent, rippling with magnetic fields and shock waves. It is in the coldest and darkest corners of this vast medium that stars are born. Star formation begins in silence. Inside enormous molecular clouds, some spanning hundreds of light years, gravity gathers material slowly, almost patiently. Regions grow dense enough to collapse inward, forming small knots that heat and glow faintly. Over time, a protostar emerges at the center, surrounded by a swirling disk of gas and dust. If the protostar continues to gather mass, its core grows hotter and more pressurized until hydrogen begins to fuse into helium. Light bursts outward. A new star ignites. Another point of brightness joins the galaxy. The Milky Way does not form stars at the rate it once did. Billions of years ago, during its most active period, the galaxy was buzzing with star birth. Enormous clouds collapsed rapidly, and clusters of massive, bright stars lit up the arms. Today, the pace is slower. Gas is thinner and more spread out. Many regions have been heated by previous generations of stars, but the process continues quietly. We live in a mature, stable era of the galaxy's life, not young and chaotic, and not yet old and fading. Even as stars form, others die, and their deaths reshape the galaxy. When a massive star collapses into a supernova, it sends shock waves through space, compressing nearby clouds and triggering the next wave of star formation. Heavy elements, carbon, oxygen, calcium, iron, and countless others, are thrown outward, enriching the interstellar medium. These are the elements that form planets, oceans, atmospheres, and life. Every breath you take, every atom in your bones, was forged long ago in the heart of a star. The Milky Way is full of structures we cannot see. Cosmic rays, high-energy particles, stream through the galaxy at almost the speed of light. Gamma rays glow around regions of violent activity. Radio waves reveal cool hydrogen gas extending far beyond the starlit disk. And then there are the mysterious Fermi bubbles, two enormous lobes of gamma radiation rising above and below the galactic center. Their cause is still debated. They may have come from a burst of star formation or from an ancient flare of the supermassive black hole at the galaxy's heart. That black hole, Sagittarius A*, lies concealed behind dense clouds of dust. Though it is more than 4 million times the mass of the Sun, it occupies a region smaller than the orbit of Mercury. We cannot see it directly, but we watch the stars around it. They whip through their orbits at dizzying speeds, tracing graceful ellipses that reveal the black hole's presence like planets circling an invisible sun. Today, Sagittarius A* is quiet, feeding only occasionally on small gas clouds. But evidence suggests that long ago, it may have been far more active, shining like a quasar, radiating intense energy, and shaping the inner regions of the galaxy. The center of the Milky Way is not smooth. It contains a bar-shaped structure made of stars, and within that bar may lie a smaller, hidden bar rotating independently. These intertwined structures help organize the motion of gas, guiding material toward the core and influencing the shape of the spiral arms. The inner galaxy is a labyrinth of intersecting orbits, bars, rings, and streams, an intricate gravitational puzzle sculpted by billions of years of motion. As we move outward from the center, the spiral arms become clearer, sweeping lines of star formation wrapped around the disk. But these arms are not solid. They are density waves, patterns of compression moving through the galaxy like slow-motion traffic jams. Stars drift in and out of them. As gas enters the wave, it compresses, ignites with new stars, and then moves on. From a distance, the arms appear fixed, but up close, everything flows. Our solar system rests in a small neighborhood called the Orion Spur, a minor lane between the larger Sagittarius and Perseus arms. It is relatively calm here. Massive stars and supernovae are less common than in the major arms, and the radiation environment is more stable. This quiet region may have been crucial for life on Earth to evolve. Too close to the core, and radiation levels might be deadly. Too far out, and heavy elements might be too scarce for planets to form. Earth lies in the galaxy's habitable zone, not by design, but by cosmic coincidence. Beyond the disk lies the halo, a faint sphere of ancient stars and clusters surrounding the galaxy. Some of these clusters are more than 12 billion years old, relics from the earliest ages of the universe. The halo is also full of dark matter, the invisible substance that outweighs all visible stars many times over. Without dark matter, the Milky Way would fly apart. Its stars would drift into space like sparks from a dying fire. We do not know what dark matter is, but we know that it holds the galaxy together, shaping every orbit, every stream, every arm. And beyond, even the halo, lie the farthest stars, lonely travelers captured from ancient galaxies long swallowed by the Milky Way. They orbit at great distances, taking billions of years to complete a single revolution, tracing out the true size of the galaxy, which stretches much farther into the night than our eyes can ever see. As you continue drifting through the quiet glow of the Milky Way, imagine yourself passing through regions no spacecraft has ever approached, places where time feels stretched, where gravity shapes the path of every dust grain, and where ancient stories linger in the motions of stars. The galaxy is not a simple whirlpool of light. It is a long, slow symphony of movement, each star a note, each orbit a rhythm, each collapse or explosion a sudden burst of sound in the cosmic score. Tonight, we travel deeper into that music. Far from the spiral arms, out in the halo, you might expect only emptiness, but the halo holds secrets. There are faint streams, ribbons of stars pulled from dwarf galaxies long ago, arching across thousands of light years. These stellar streams curve like ghostly trails, their stars moving together with the same momentum, relics of galaxies dissolved by the Milky Way's pull. They trace paths like the faded handwriting of ancient events. Even now, astronomers discover new streams, new loops of forgotten light drifting quietly through the outskirts. And then there are the globular clusters, tight, shimmering spheres of hundreds of thousands of stars. They orbit not in the flat disk, but in wide arcs above and below it, ancient and nearly ageless. Some are older than the Milky Way itself, formed in primordial clouds before our galaxy had a disk or arms or a center shaped by bars. These clusters are stable, resilient, slow to change. They glow with warm, golden hues, evidence of their old age, and they drift through the halo like lanterns suspended in the dark, carrying memories from epochs before our sun was even imagined. Not all stars move with the galactic rotation. Some orbit backward, in retrograde, drifting against the flow like solitary travelers refusing to follow the crowd. These stars likely came from galaxies long since consumed, foreign bodies preserved in motion. Their paths are clues, traced backward to collisions we cannot see directly. They are reminders that the Milky Way is not a single native population, but a mosaic of histories. And in the immense quiet between these wanderers float rogue planets, worlds without stars. These planets have been ejected from their solar systems long ago, flung into the dark by gravitational encounters or the violent end of a star. They drift alone, warmed only by their own internal heat, unlit and nearly undetectable. Some of these lonely worlds may carry oceans beneath thick ice, hidden from the cold of space. Though they seem adrift, they too are part of the galaxy's story. If you move closer to the galactic disk again, you encounter the interstellar medium, the thin but complex ocean of gas that fills the space between stars. It is not truly empty. Hydrogen atoms, dust grains, charged particles, and magnetic fields weave a tapestry more dynamic than it appears. Vast cavities called superbubbles mark the regions where groups of stars have exploded in succession. Shock waves carve spherical hollows. Hot gas rises from these bubbles like a chimney into the halo before cooling and raining back down into the disk, a galactic fountain that cycles material between the layers. This cycle enriches the galaxy. Heavy elements born in supernova are lifted into the halo, scattered across great distances, and later return to join new clouds. The Milky Way breathes through these chimneys, exhaling heat, inhaling cooled gas, maintaining the long-term balance necessary for new generations of stars. One of the most striking structures in the galaxy lies at its center, Sagittarius A*, the supermassive black hole. It rests quietly now, but the evidence around it reveals a more active past. The vast Fermi bubbles that extend above and below the disk may be remnants of a time when the black hole flared brilliantly, devouring matter and unleashing jets of energy. Today, the stars closest to it orbit at unbelievable speeds. Some complete an orbit in mere decades, tracing small loops of astonishing precision. Watching them feels like watching the galaxy's heartbeat. But the center is also home to something stranger, the galactic bulge. When mapped carefully, it reveals a peanut-like shape, not a sphere but a thickened, split structure carved by the dynamics of the rotating bar and heated by the motions of billions of stars. The bulge is full of ancient suns, densely packed, moving in intricate patterns. Here, the galaxy's history overlaps with its future as old stars fade while gas is funneled inward, potentially feeding new bursts of activity. Farther out, the sun moves through the disk not in a perfectly flat orbit, but bobbing up and down, crossing the galactic plane every tens of millions of years. This motion is subtle but persistent. Some scientists have wondered whether this oscillation might occasionally expose Earth to higher levels of cosmic radiation, but the evidence remains uncertain. What is certain is that even our familiar solar system participates in the galaxy's restless dance, never still, always in motion. Magnetic fields weave through the disk, threading through gas clouds and shaping the arcs of dust. Though weak by earthly standards, they guide the flow of charged particles and influence how clouds collapse. In some regions, dust grains align with these magnetic fields, polarizing the starlight that passes through. In others, the fields twist into loops and filaments, tracing patterns that look like ripples across invisible water. Everywhere, the galaxy radiates energy. X-rays glow around compact objects, neutron stars siphoning material from companions, white dwarfs flaring with accretion bursts, and black hole binaries feeding silently. Cosmic rays rush through space, carrying traces of the violent processes that created them. Even neutrinos, a trillion pass through your body every second, whisper from the hearts of stars. And then there is dark matter. Though unseen, it dominates everything. It forms the halo that surrounds the galaxy. It shapes the rotation curve, ensuring that stars in the outer disk move almost as fast as those near the center, something that Newtonian physics cannot explain with visible matter alone. It guides mergers, catches streams, and bends orbits. Without dark matter, the Milky Way would unravel like a loose thread. When you look at the sky from Earth, you see only 0.00003% of the galaxy. Just a faint band, a narrow projection of the disk as viewed from inside. It took centuries to understand the shape we belong to. Even now, with missions like Gaia mapping billions of stars in precise detail, the Milky Way remains partly hidden. Dust blocks our view. Distances distort easily. Structures blend. And the galaxy stretches far beyond what the naked eye or simple telescopes can reveal. Yet standing on Earth, gazing upward, you are seeing the inner spine of the galaxy, a glowing river of stars. You're looking along the disk, through layers of starlight, gas, and dust stacked so densely that they blend into a continuous pale band. The fact that you cannot see its true size or shape only adds to its mystery. Every star you see is part of a long story, one that began before the Earth existed, before the sun ignited, before the galaxy completed even a fraction of its current form. And every atom in you, every carbon molecule, every oxygen atom, every metal ion, was shaped in stars that lived and died long before our world formed. You are not just in the galaxy, you are made of it. As you continue drifting softly through the Milky Way, imagine gliding past regions shaped not by stars or dust alone, but by the grand architecture of gravity, time, and cosmic motion. The galaxy feels serene from afar, but within its arms, currents of matter and energy weave endlessly, forming patterns that stretch across millions of years. If you let yourself sink into this calm, you begin to sense that the Milky Way is not just a place. It's a story unfolding in slow motion. The spiral arms you drift alongside are not fixed roads of stars, but traveling waves. They move at a different pace than the stars themselves, like traffic jams flowing through an endlessly turning highway. A star might spend tens of millions of years inside an arm, shining brightly, before drifting out into a quieter region. New stars ignite within the arms as gas becomes compressed. Old stars glide out as the density wave passes on. The arms are illusions of structure, patterns formed not of individual objects but of motion, rhythm, and gravity. Within these arms lie stellar nurseries, vast clouds of cold hydrogen and molecular gas, dark to the eye, yet full of potential. They do not glow until starlight ignites within them. Some clouds remain starless for millions of years, suspended in silence, waiting for a shock wave or tidal squeeze to trigger collapse. Others glow in infrared light as embedded stars warm their surroundings. If you could watch the galaxy in time-lapse, these clouds would pulse and reshape like breath, expanding, collapsing, rippling under the influence of unseen forces. Supernova explosions act like cosmic storms, stirring this gas, spreading heavy elements, and altering the chemistry of entire regions. Their shock waves ripple outward for hundreds of light years, triggering new star birth in some pockets while dispersing gas in others. The galaxy's evolution depends on this process: collapse, ignition, death, dispersal, renewal. Without supernovae, the Milky Way would be static, chemically poor, and unable to form complex planets. With them, the galaxy becomes a recycling engine, constantly forging and reforging the ingredients of cosmic life. As you drift farther, the scale of the galaxy becomes more apparent. Every point of light that seems still is actually moving. Even the sun, so steady to human senses, is gliding through the disk at incredible speed. Its orbit takes hundreds of millions of years, tracing a path through arms, gaps, voids, and regions of varying density. The sun also rises and falls through the galactic plane in a slow oscillation, like a cork bobbing gently in water. This up and down motion is subtle but eternal, shaped by the gravity of the disk and the mass distribution around it. Some researchers once wondered whether this vertical oscillation might influence conditions on Earth, perhaps by exposing the solar system to bursts of cosmic rays when it moves farther from the protective dust of the plane. While evidence is inconclusive, the idea illustrates how deeply connected everything is. The sun does not move alone. It is part of the galaxy's long, looping heartbeat. The galaxy's gravitational field exerts tidal forces on clusters, dwarf galaxies, and streams. Just as the moon pulls tides on Earth's oceans, the Milky Way pulls on everything within it. Star clusters can be stretched into elongated shapes or stripped entirely, their stars smeared into long streams. Dwarf galaxies orbiting us, like the Sagittarius dwarf, are torn apart slowly, their stars added to the halo. Over billions of years, the galaxy reshapes its companions, incorporating them strand by strand. These tidal interactions give the Milky Way its irregularities. The disk is not symmetrical. One side is thicker, some arms brighter, others thinner or more fragmented. The warp itself may be a consequence of external gravitational nudges. The halo is lopsided, too, denser in some regions, thinner in others, shaped by ancient collisions with satellite galaxies or dark matter clumps drifting unseen through the outer reaches. Dark matter, though invisible, forms the backbone of the galaxy. It stretches far beyond the luminous disk, creating a gravitational well so deep that every star, planet, and cloud is trapped within it. It surrounds the galaxy in a vast halo extending hundreds of thousands of light years. Without this halo, the Milky Way's outer stars would drift away. With it, the galaxy holds together in an elegant, spinning equilibrium, a disk suspended in an invisible sphere of mass. The Large and Small Magellanic Clouds, two dwarf galaxies, may be newcomers to the Milky Way's gravitational family. For decades, they were believed to be long-term companions, but new measurements suggest they might be on their first approach. Their arrival has stirred the outer disk, perhaps contributing to the warp. A long ribbon of gas, the Magellanic Stream, trails behind them, stripped by tidal forces and pressure from the galactic halo. This stream arcs across the southern sky, invisible to the naked eye, but immense in radio wavelength maps. One day, perhaps, this gas will fall into the Milky Way, fueling new waves of star formation. Deeper inside the galaxy, radio waves reveal structures hidden by dust, cold hydrogen spirals, enormous cavities, and intricate filaments shaped by magnetism. Radio telescopes map these patterns with clarity that optical telescopes cannot match. Even the spiral arms themselves are easier to trace in radio wavelengths, where gas shines more clearly than stars. The galaxy, when seen in radio light, looks less like a smooth swirl and more like a dynamic river network, streams, eddies, and currents forming a turbulent but majestic whole. The Milky Way's heart is a hub of complexity. Near Sagittarius A*, stars crowd together, moving at extreme speeds. Infrared observations show their orbits, tight loops that chart the invisible gravitational monster at the center. Occasionally, a gas cloud wanders too close, swirling inward, heating intensely, and flaring with X-rays before disappearing beyond the event horizon. Most of the time, the black hole is quiet, but the occasional flicker reminds us of its lurking power. The bulge around it swells into a peanut-like shape when viewed from afar. This shape emerges because the stars in the inner disk form a bar, and that bar thickens over time as orbits buckle upward. Inside the bar may lie a smaller, secondary bar rotating independently, a nested structure that influences the inflow of gas and shapes the surrounding arms. Orbiting farther outward, the Sun and its neighbors glide through a region called the Orion Spur. It is not a major arm, but a minor lane between two great ones. Here, radiation levels are moderate, and star formation is active but not overwhelming. This calm neighborhood may be one reason life could evolve on Earth. Too close to the core, and the galaxy becomes chaotic. Too far out, and the chemical richness needed for Earth-like planets becomes scarce. Beyond the disk lies the halo, home to ancient stars, globular clusters, and dark matter. Halo stars often follow elongated, tilted orbits, moving in patterns that seem disconnected from the disk. Many were born in smaller galaxies before being captured. By studying their motions, astronomers can trace the history of past mergers, reconstructing the Milky Way's growth like archaeologists studying scattered artifacts. Every halo star is a messenger from a different era. Far beyond even the halo lie the galaxy's most distant residents, stars orbiting at the very edge, some likely captured from galaxies long since dissolved. Their paths are so vast that a single orbit may take billions of years. They mark the boundary between the Milky Way and the intergalactic medium, the thin, hot gas that fills the space between galaxies. And yet, despite all its complexity, the Milky Way feels like a single, unified structure, a cosmic city with districts, neighborhoods, highways, and suburbs, all connected through gravitational threads. It is ancient but evolving, enormous but delicate, calm yet filled with quiet storms. Everything you are, every atom, every breath, comes from processes within galaxies like this one. You are made of recycled stardust, shaped by the quiet unfolding of cosmic time. Tonight, as you drift deeper into sleep, the Milky Way continues turning, stars are forming, and light is crossing unimaginable distances. And you, floating in a small orbit within one arm of this luminous wheel, are part of its gentle, endless story. As you drift deeper into the Milky Way, imagine descending through layers of starlight the way a diver moves through levels of an ancient ocean. Each depth reveals new structures, eddies of gas, swirling schools of stars, and faint trails left by long-forgotten currents. The galaxy is not a rigid machine, but a living, evolving tapestry. The deeper you travel, the more clearly its history begins to speak. Picture yourself gliding past a region where stars seem strangely crowded. These aren't ordinary clusters or spiral arm neighborhoods. These are the remains of ancient collisions. Long ago, dwarf galaxies approached the Milky Way and were torn apart. Their stars didn't vanish, they were folded in. Some became part of the thick disk. Others became halo wanderers. And still others formed enormous, sweeping streams. If you could trace their orbits backward, you would see them converging into small, compact shapes, the galaxies they once were. One such event is known as the Gaia-Enceladus or sausage merger. Though invisible to the eye, its signature is etched into the motion of stars. These stars move in elongated, looping paths that slice through the disk at odd angles. They are survivors of a galaxy the Milky Way swallowed billions of years ago. Its death reshaped our own galaxy, thickening the disk, stirring the halo, and altering the early rotation curve. Even our sun may owe its birthplace to the turbulence this merger caused, as gas clouds were compressed and new stars ignited in the wake of that cosmic collision. And so you drift onward, realizing that the Milky Way is stitched from the remnants of dozens, perhaps hundreds, of smaller galaxies. Every few 100 million years, another dwarf galaxy wanders too close and is pulled apart like threads unraveling from a cloth. Their stars scatter softly into the halo, forming thin arcs that slowly stretch into long, faint lines. Over time, these lines blur, mixing with the population of the halo until only subtle chemical fingerprints remain. Chemistry, in fact, is one of the galaxy's greatest storytellers. Every star carries a chemical signature, its own unique pattern of elements. Some are rich in heavy metals, formed from gas enriched by multiple supernovae. Others are almost pure hydrogen and helium, born before the universe had produced much else. By reading these signatures, astronomers can reconstruct a star's origins. Stars formed together share similar fingerprints. Stars from merged galaxies show distinct mixtures. Chemistry becomes a map, a language written in atomic ratios, revealing the hidden genealogy of the Milky Way. You glide into a region filled with delicate ribbons of starlight, stellar streams. Some stretch across the sky for tens of thousands of light years. To the naked eye, each might look like a faint, thin cloud, but when mapped precisely, they reveal themselves as the stretched-out remains of clusters and small galaxies. One of the most striking, the GD1 stream, is a thin golden thread extending across a vast portion of the halo. Another, the orphan stream, loops with no obvious surviving parent, its original cluster long since scattered. These streams are cosmic fossils, tracing out unseen gravitational contours, marking where structure once existed. As you drift along one such stream, you feel a gentle tug, the kind of gravitational whisper that shapes orbits. This pull may come from something you cannot see, perhaps a clump of dark matter, drifting silently in the halo. These clumps leave disturbances in streams, small gaps or kinks that betray their presence. Though invisible, dark matter sculpts the galaxy's skeleton, influencing the flow of stars, gas, and entire arms. Chemistry, in fact, is one of the galaxy's greatest storytellers. Every star carries a chemical signature, its own unique pattern of elements. Some are rich in heavy metals, formed from gas enriched by multiple supernovae. Others are almost pure hydrogen and helium, born before the universe had produced much else. By reading these signatures, astronomers can reconstruct a star's origins. Stars formed together share similar fingerprints. Stars from merged galaxies show distinct mixtures. Chemistry becomes a map, a language written in atomic ratios, revealing the hidden genealogy of the Milky Way. You glide into a region filled with delicate ribbons of starlight, stellar streams. Some stretch across the sky for tens of thousands of light years. To the naked eye, each might look like a faint, thin cloud, but when mapped precisely, they reveal themselves as the stretched-out remains of clusters and small galaxies. One of the most striking, the GD1 stream, is a thin golden thread extending across a vast portion of the halo. Another, the orphan stream, loops with no obvious surviving parent, its original cluster long since scattered. These streams are cosmic fossils, tracing out unseen gravitational contours, marking where structure once existed. As you drift along one such stream, you feel a gentle tug, the kind of gravitational whisper that shapes orbits. This pull may come from something you cannot see, perhaps a clump of dark matter, drifting silently in the halo. These clumps leave disturbances in streams, small gaps or kinks that betray their presence. Though invisible, dark matter sculpts the galaxy's skeleton, influencing the flow of stars, gas, and entire arms. The disk itself holds another mystery: the difference between the thick and thin components. The thick disk, older and richer in stars with strange orbits, likely emerged from early periods of chaotic merging. The thin disk formed later, settling into an orderly plane. Stars with higher metallicity and circular orbits glow softly here, forming the familiar spirals that define the Milky Way's shape. As you move through this disk, you feel the subtle vibration of passage through a spiral arm, a density wave, not a solid structure. Gas compresses around you. Young stars cluster in glowing nurseries. Dust absorbs starlight, blocking entire regions from view yet enabling molecules to form inside its shadows. The cold, dark pockets of the arm cradle newborn stars, just as similar regions once cradled the infant sun. The sun was not born alone. It emerged from a stellar cluster, hundreds or even thousands of stars sharing the same birth cloud. Over time, gravitational tugs from other stars, giant molecular clouds, and the tidal pull of the Milky Way dispersed the cluster. The sun's siblings now wander the galaxy, scattered across thousands of light years. Somewhere in the night sky, among the distant points of light, there may be stars with the same chemical fingerprint, formed from the same enriched nebula that gave birth to the sun and to the early solar system. Finding them is like searching for long-lost family in a city of 200 billion strangers. Drifting farther outward, you rise above the galactic plane and into the halo, where globular clusters orbit like ancient sentinels. These clusters are made of hundreds of thousands of stars, bound tightly together in luminous spheres. Their cores are so dense that stars occasionally collide or merge, forming unusual objects like blue stragglers, stars that appear too young for their surroundings. These clusters act as living archives. Their stars are some of the oldest in the universe, with compositions close to the primordial elements formed just after the Big Bang. Yet even these clusters are vulnerable to the galaxy's tides. Over billions of years, some clusters have been stretched into streams, their stars peeled away like threads from a rope. Others have survived intact, circling the galaxy in elegant orbits. As you glide through the halo, you notice enormous hollow bubbles, spherical cavities carved by past waves of star formation. These giant shells expand slowly, hundreds of light years across. Inside them, gas is thin and warm. At their edges, material piles up, forming dense ridges where new stars may one day ignite. These structures are the fossils of cosmic storms, echoes of times when clusters of massive stars were born together, lived brief but brilliant lives, and exploded in rapid succession. Below you, dust grains drift through the halo like ash on a breeze. Many contain complex organic molecules, carbon-based compounds formed in dying stars and frozen onto tiny mineral grains. These grains may carry alcohols, sugars, and aromatic hydrocarbons. Though not alive, they are the raw ingredients from which life can emerge. When these grains fall into collapsing clouds, they become part of the material that forms new solar systems. Some may have seeded Earth during its early history. You float onward, watching as the galaxy rotates slowly beneath you. Its arms twist like luminous vines. Its outer regions ripple with subtle asymmetries. Its core glows with energy, and yet everything seems peaceful from this high vantage point. Galaxies collide. Stars are born. Clouds collapse. Dark matter shapes the invisible. Dust carries potential, And through all of this, the Milky Way remains a place where light and shadow mingle across billions of years. As you drift back toward the disk, you sense how profoundly connected everything is. The sun's orbit, the tilt of the disk, the collapse of clouds, the glow of nebulae, the scattering of streams, all part of the same vast story. And you, floating gently through this narrative, are made of the same elements that shaped it. As you continue gliding through the Milky Way, imagine yourself drifting close to the galactic midplane, a region dense with starlight, but woven with dark filaments of dust. These dust lanes stretch like ink strokes across the luminous disk, hiding entire constellations, concealing star-forming regions, and shaping the galaxy's glow. They appear as shadows from Earth's perspective, yet within these shadows lie some of the most active and energetic processes in the galaxy. Dust grains here are tiny, mere fractions of a micron, yet they play an enormous role. They shield fragile molecules from harsh ultraviolet radiation. They cool gas clouds, allowing them to collapse more easily. They absorb starlight and re-emit it in infrared wavelengths, turning dark clouds into warm, glowing sculptures when viewed with the proper instruments. These clouds, some tens or hundreds of light years wide, cradle the seeds of future stars, planets, and even life. As you pass through one of these dense clouds, the starlight dims. The air, if there were air, would feel heavy with unseen particles. Yet the silence is peaceful. No turbulence touches you here except the slow drift of gas. The temperature drops to just a few degrees above absolute zero. Everything feels suspended in time. And deep inside this quiet darkness, gravity works patiently, drawing atoms inward, creating the faint structures that will one day form entire solar systems. Now imagine drifting toward a region where the quiet breaks, not with sound, but with motion. Here lies the aftermath of a supernova, a stellar explosion that has carved out an enormous cavity in the interstellar medium. Hot gas, millions of degrees in temperature, flows outward like a silent storm, pushing dust aside, sculpting arcs and shells that glow faintly in the ultraviolet. Supernova remnants like this one act as engines of change. Their shock waves trigger star formation in nearby clouds. Their ejecta scatter heavy elements, iron that will one day flow in the blood of living creatures, oxygen that will form planets' atmospheres, silicon that will build rocks and mountains. You glide along the edge of this expanding bubble and see the shimmering boundary where hot gas meets cooler regions. The interface ripples, curling like smoke. Magnetic fields thread through the gas, guiding the shock front, shaping the remnant into filaments and knots. Over tens of thousands of years, this structure will expand, cool, and blend into the surrounding medium, leaving behind only subtle chemical traces. You drift further and sense the cosmic radiation passing through you, high-energy particles traveling close to the speed of light. They come from supernova remnants, from distant galaxies, from unknown accelerators scattered through the universe. They are so small you feel nothing, yet they carry within them the story of powerful forces. Every second, cosmic rays cross the galaxy, passing through stars, planets, and even your body. They are reminders that the cosmos is active, filled with invisible currents. Now your path begins curving inward, toward the galactic center. The density of stars increases. What once were sparse points of light now form a thick golden glow. Stellar orbits twist and tilt. Some stars move in tight ellipses, others in eccentric loops. The gravitational field here is intense, sculpted by a mixture of stars, gas, and the enigmatic mass of the central black hole. The closer you drift, the more clearly the influence of Sagittarius A* can be felt, not as a force pulling on you, but as a quiet structure organizing the motion of everything around it. At the heart of the galaxy lies this supermassive black hole, 4,000,000 times the mass of the Sun. You cannot see it. It emits no light of its own, but the stars around it reveal its presence. They swing in tight orbits, completing circles in just a few decades. Their paths are mapped with exquisite precision, forming an elegant choreography around an invisible anchor. Occasionally, a small gas cloud wanders too close. As it falls inward, it heats to millions of degrees, emitting bright X-ray flares before vanishing beyond the event horizon. These flares are brief, minutes or hours, but they reveal the black hole's still beating heart. For most of the time, Sagittarius A* is quiet, almost sleepy, but signs across the galaxy suggest it was not always so peaceful. The massive Fermi bubbles, two giant lobes of gamma radiation stretching above and below the galactic plane, are thought to be relics of an ancient outburst, a time when the black hole consumed large amounts of gas and emitted powerful jets. You drift outward again and pass through the peanut-shaped bulge. Stars here are old, densely packed, and moving in patterns shaped by the galactic bar. The bar itself is a long, rotating structure of stars that stretches across the center like a glowing bridge. It funnels gas inward, feeding the central regions and shaping the spiral arms. Bars are dynamic, forming, dissolving, reforming, and the one in the Milky Way may be only one part of an even more complex nested structure. Deep inside it may lie a smaller bar rotating at a different angle, influencing orbits in ways not yet fully understood. Then, as you drift farther from the core, the view opens into the broad sweep of the disk. Here, stars of all ages shine: young blue giants, middle-aged suns, ancient red dwarfs. Their orbits form a vast carousel. Some move in nearly perfect circles, others follow gentle ellipses. The pattern is governed by gravity and moderated by the unseen influence of dark matter. Without dark matter's stabilizing pull, the outer disk would fly apart. With it, the galaxy spins like a balanced wheel. You move toward a region where the disk subtly warps upward, a gentle bend, thousands of light years across. This warp rotates slowly, influenced by interactions with satellite galaxies, by dark matter ripples, and by the long-term motion of the disk. It is an elegant reminder that even structures on cosmic scales are flexible, breathing gently across time. Beyond the warped edge, stars grow sparse. You are entering the stellar halo again, a region so faint it barely glows. Here lies a mix of ancient stars, globular clusters, and streams stretched like cosmic fingerprints. Some stars in this region orbit on steeply tilted paths. Others travel in vast loops. Many were born in galaxies long since absorbed by the Milky Way, immigrants drifting far from their original homes. You pass one such ancient traveler, a star older than most of the galaxy. Its light is faint, tinged with the warm hue of old age. Its chemical fingerprint reveals almost no metals, a sign that it formed shortly after the Big Bang, before the universe had time to build heavy elements. This star has survived gravitational upheavals, tidal stripping, and billions of years of cosmic evolution. It drifts quietly now, a relic of the universe's earliest dawn. As you drift away from it, a sense of scale washes over you. The Milky Way is vast beyond comprehension. Its halo reaches out for hundreds of thousands of light years. Its disk contains billions of stars. Its arms sweep across unimaginable distances. Yet it all holds together, barely, thanks to dark matter. And through the quiet turning of the galaxy, every event, every orbit, every collapse influences the next. Galactic evolution is not a single story, but millions of overlapping ones. Stars forming, shining, dying. Dust drifting, cooling, collapsing. Gas rising and falling in fountains. Dark matter shaping the unseen architecture. Clusters merging, dwarf galaxies dissolving, streams stretching into arcs. And you, floating through this grand design, are made of material forged by all these processes. Atoms sculpted by explosions, cooled in clouds, and woven into your body through the long, intricate chain of cosmic history. In every breath you take lies the memory of stars. As you drift deeper into the Milky Way's gentle glow, imagine floating through regions where the galaxy structure becomes less like a map and more like a feeling, subtle gradients in starlight, faint currents of magnetic fields, delicate ripples that stretch across thousands of light years. The further you move from familiar constellations and known landmarks, the more the galaxy begins to feel like an immense organism, breathing slowly across time. The interstellar medium here is a complex landscape. Though thin compared to air, it is rich with features. Warm ionized gas from star-forming regions, cold pockets where molecules drift in near-perfect silence, and warm neutral clouds that thread between spiral arms. It is in these spaces that turbulence reigns, not the chaotic turbulence of stormy weather, but a slow, majestic turbulence driven by supernova explosions, shock waves, magnetic fields, and gravitational tides. You glide into a filament, an elongated thread of dense gas stretching for hundreds of light years. These filaments form the backbone of star-forming regions. They're long, narrow. Structures are shaped by gravity pulling material along magnetic channels. Some filaments are quiet, storing mass for future collapse. Others glow faintly in infrared as newborn stars warm their surroundings. Observing them feels like drifting through the root system of a cosmic forest. A little farther ahead, you find a superbubble, a giant hollow cavity carved by the combined winds of massive stars. Dozens of bright, short-lived giants once lived in this region. Their radiation sculpted the surrounding gas, pushing it outward into walls that shine faintly when ultraviolet light strikes them. Then, as these giants reached the ends of their lives, they exploded in supernova events. Each explosion expanded the bubble farther. Over time, multiple superbubbles can merge, creating massive voids in the interstellar medium. These bubbles are not empty. They are filled with hot, thin gas and threaded by magnetic fields. Sometimes, they punch through the galactic plane, forming chimneys that vent energy into the halo. Through these chimneys, material cycles from the disk to higher regions before cooling and falling back. This galactic fountain connects the layers of the galaxy like a slow, rhythmic breath. Leaving the bubble behind, you drift toward a region of the disk where old and new stars intermingle. In this quiet section, you notice how differently stars age. Blue, massive stars burn intensely but briefly, often only for a few million years. Yellow stars like the sun shine steadily for billions. Red dwarfs, the most common stars in the galaxy, burns so slowly that none born since the universe began have yet reached old age. These small red stars may one day outlive every giant, glowing softly trillions of years into the future while the Milky Way transforms around them. Some of these dwarfs host planets. Many may host systems teeming with rocky worlds or frozen spheres. Whether life can exist around such stars is still a mystery, but the galaxy provides plenty of opportunity. The Milky Way contains more planets than stars, billions upon billions of worlds drifting through all corners of the disk. Some orbit in stable zones. Others exist in harsh radiation fields. Some may be ocean worlds. Others might be carbon planets, iron planets, or exotic worlds unlike anything seen in our solar system. As you pass a small red star, you feel the hush of its faint glow. Its planets, if it has any, would bask in a dim, warm light. The star is smaller than Jupiter, yet far more massive. Its gravity binds its system tightly. If life exists here, it would live in twilight, gentle, steady, unchanging. You drift onward and sense the magnetic fields threading through the disk. These fields are invisible but powerful, shaping the motion of charged particles. They guide cosmic rays, influence the collapse of clouds, and sculpt gas into long, narrow structures. From afar, they seem like subtle patterns woven into the galaxy's fabric. Up close, they feel like tension lines stretching across the disk, connecting regions thousands of light years apart. Then you come upon a region where the galaxy has recorded a violent story, the remnants of a neutron star collision. These rare events are among the most powerful in the universe. When two neutron stars spiral together, they release intense gravitational waves that ripple across galaxies. In the final moments, as they collide, they create heavy elements: gold, platinum, uranium, materials essential for planets and perhaps for civilizations. These elements spread outward into the galaxy, eventually mixing into new clouds from which future solar systems will form. If you could watch such a collision from a safe distance, you would see a flash brighter than thousands of suns, followed by expanding debris that glows in every wavelength of light. What remains might be a larger neutron star, or, if massive enough, a new black hole. These events are rare, but their signatures can be found in stars enriched with heavy elements. Every gold atom on Earth may have originated in an explosion like this. You drift past the region, sensing the quiet aftermath, and move toward the outer disk. Here the star density thins. Gas clouds stretch out more sparsely. Spiral arms become harder to distinguish. The warp of the disk grows more visible, bending upward like the edge of a leaf. The gravitational pull from the Magellanic Clouds and dark matter substructures help create this distortion. Over millions of years, the warp will shift and rotate, responding to external forces like a slow-motion wave crossing a pool. Beyond the warped edge, the galaxy grows faint. You enter the realm of the outer halo. Here, stars are rare and widely spaced. Many orbit on steeply inclined paths. Some plunge through the disk every few 100 million years. Others remain in the halo, never coming close to the bright inner regions. You pass by a globular cluster drifting in a slow orbit around the galactic center. Its stars are tightly packed, gleaming like a jewel suspended in night. Their orbits trace intricate patterns near the cluster's core. Some stars exchange mass with companions, forming unusual and sometimes unstable systems. Over time, gravitational interactions push some stars outward, populating the halo with cluster escapees. As you move beyond the cluster, the halo thins even more. You begin to see the boundaries of the Milky Way, regions where its gravitational influence fades into the intergalactic medium. The outermost stars orbit so slowly that completing a single loop may take billions of years. Some of these stars were captured from other galaxies. Others may be remnants of dwarf galaxies long since devoured. You sense the dark matter halo enfolding everything. Though invisible, it dominates the outer regions. Its gravitational pull keeps the galaxy intact against the centrifugal force of rotation. Without dark matter, the outer disk would unravel. With it, the Milky Way spins like a great wheel suspended in an invisible sphere. Everywhere you drift, the galaxy whispers of continuity. Star birth leads to star death. Death feeds new clouds. Clouds collapse into new stars. Elements cycle through generations. Clusters dissolve. New clusters form. Streams trace old histories. Bars rotate. Arms shift. Halos grow and absorb. The galaxy changes, yet somehow remains whole. And through this vast, slow transformation, the atoms that one day became you traveled their own ancient journey, fused in stars, scattered into space, cooled in clouds, incorporated into a new solar system, and eventually assembled into a living being capable of reflecting on its cosmic origins. You are drifting through your own history. The galaxy is not separate from you. It is your ancestor, your home, your source. As you drift near the quiet outer layers of the Milky Way, imagine the galaxy not as a single isolated island of stars, but as part of a vast cosmic archipelago. The Milky Way moves through space with companions, dwarf galaxies bound by gravity, streams of stars tracing past collisions, and remote clusters orbiting like distant memories. Everything you see is connected by the long, slow choreography of galactic evolution. Far above the disk, where the halo grows faint, you find the Sagittarius dwarf spheroidal galaxy, one of the Milky Way's closest companions. It is stretched and distorted, slowly dissolving as the Milky Way pulls its stars outward. Over billions of years, it has been stripped again and again, its stars forming long streams that wrap around the galaxy like ghostly ribbons. These streams remind you that galaxies grow not by sudden accretion, but by endless, patient absorption. Other companions drift nearby. The small and large Magellanic Clouds, two dwarf irregular galaxies, float like cosmic lanterns in the southern sky. They are rich in gas, forming new stars at an impressive rate. As they orbit the Milky Way, they leave trails of hydrogen behind, forming the Magellanic Stream. This enormous ribbon of gas curves across the sky, invisible to normal vision but vast in radio wavelengths. Eventually, much of this gas may fall into the Milky Way, feeding new waves of star formation. Drifting along this stream, you sense its history. It contains signatures of both Magellanic Clouds, as well as hints of interaction with the Milky Way's halo. Ram pressure stripping, gas being removed due to motion through hot, diffuse halo plasma, has shaped it. Tidal forces stretch it. Radiation from hot stars in the clouds ionizes parts of it. The stream is a flowing document of interactions between galaxies, a dynamic structure shaped by motion and pressure rather than solid boundaries. Nearby floats the Magellanic Bridge, a stream of gas and stars connecting the two clouds. This bridge is relatively young, perhaps only a few 100 million years old, and formed in a close encounter between the two dwarf galaxies. If you drift along it, You find young stars formed directly from the disturbed gas, glowing faintly in a structure that did not exist before that encounter. You glide onward and sense the gravitational influence of dark matter subhalos, small, dense clumps that formed early in the universe. Many contain no stars at all, yet their presence shapes the paths of stellar streams, carving tiny gaps and distortions. These silent objects act like passing ships disturbing the wake of a calm sea. They prove that much of the Milky Way's mass remains unseen, detectable only through its pull. Entering the outer halo, you encounter ultra-faint dwarf galaxies, collections of only a few thousand stars. Some are so dim that they were discovered only recently. These tiny galaxies are ancient, relics from the universe's youth. Their stars contain extremely low levels of metals, suggesting they formed before the first generations of stars seeded the cosmos with heavy elements. In these dwarfs, you find clues to the early universe, preserved in isolation for billions of years. Drifting back toward the disk, you see the spiral arms from a new perspective. Their curvature is elegant, their spacing nearly rhythmic. Yet they are not fixed shapes. They shift, break, reform. Density waves pass through the disk, guiding gas into new patterns. Spiral arms may be triggered by interactions with satellite galaxies or by instabilities within the bar. They are not permanent features, but long-lived, slowly migrating structures. Passing through one arm, you pass clusters of bright blue stars. These giants burn hot and live briefly. Their light sculpts nearby gas into glowing nebulae. Their winds push material outward in arcing shells. Some are destined to explode as supernovae within a few million years, injecting energy and heavy elements into the surrounding space. You sense the slow tension building in their cores, fusion pushing heavier and heavier elements together until collapse becomes inevitable. Nearby sits a stellar nursery, shadowed and cool. Here, gas is dense enough to collapse into new stars. Dust blocks visible light, turning the region into a dark silhouette against the brighter backdrop of the arm. Inside these clouds, molecular hydrogen and carbon monoxide trace long filaments. Gravity knots sections of these filaments into protostars. Each protostar is surrounded by a swirling disk of gas and dust, the raw material of future planets. As you float gently across this region, you see the earliest stages of planetary systems forming. Dust grains collide and stick together, forming pebbles. Pebbles become rocks. Rocks become planetesimals, small bodies like asteroids. Over millions of years, some grow into full planets, carving gaps in the protoplanetary disk as they sweep material away. Jets of gas shoot out from the poles of the young stars, clearing paths and regulating growth. Further along the spiral arm, you find an older cluster, its brightest stars already gone supernova. The remaining stars are less massive, quieter. Some are red giants, slowly fusing helium into heavier elements. Others are white dwarfs, cooling embers of once bright suns. Their light is faint, but their gravity remains strong. They travel together through the disk, remnants of their shared birth long ago. Drifting deeper into the arm, you feel pockets of turbulence. Gas swirls around as gravity competes with pressure. These turbulent regions shape the distribution of star formation. In some areas, turbulence slows collapse, holding gas aloft. In others, turbulence compresses material, triggering rapid star formation. The result is a patchwork of quiet and active regions, clouds where nothing happens for millions of years, lying beside clouds that ignite in bursts of new stars. You move toward the galactic bar again, sensing how it redirects gas. Gas flows inward along lanes shaped by the bar's rotating gravitational field. At certain resonances, specific regions where orbital speeds align with the bar's rotation, gas piles up, forming rings. These rings can host intense star formation or act as reservoirs feeding the central black hole. Stepping slightly inward from the bar, you enter the mysterious X-shaped bulge. Stars here move on orbits that bend and twist, forming a three-dimensional structure that resembles two wings spreading outward. This shape is carved by the bar's evolution. Stars pushed into vertical orbits by instabilities over billions of years. From the right angle, the bulge glows like a cosmic lantern, subtly tracing this peanut-like contour. As you drift away, the disk stretches out beneath you again. You glide above lanes of stars that spiral outward into the quiet frontier of the galaxy. Here, radial migration becomes evident. Stars do not stay fixed at their birth radii. Over billions of years, interactions with spiral arms and bars push some inward, others outward. The Sun itself may have migrated significantly since its birth. This migration mixes the disk, blending stars of different ages and compositions into a rich mosaic. Passing into the thick disk, you notice the increase in stellar velocity dispersion. Stars here move faster, with more vertical motion. They are older, many formed during the chaotic early days of the Milky Way. Their orbits are tilted and eccentric. Some belong to early merger events. Others are relics of the proto-galactic cloud that birthed the Milky Way before it settled into a disk. Deeper still, you reach the realms where cosmic rays flow freely. They trace magnetic field lines, carrying energy across the galaxy. Though invisible, they interact with gas, heating it and influencing star formation. They also shape the chemical evolution of clouds, ionizing atoms and triggering reactions. Without cosmic rays, the chemistry of the interstellar medium would be far simpler, and star formation might proceed differently. Finally, as you rise once more toward the halo, the galaxy fades into soft gradients. The arms blur. The bar disappears beneath a veil of starlight. The halo stretches, filled with silent wanderers. Everything becomes calm. The Milky Way spins gently below you, a luminous whirlpool suspended in darkness, breathing slowly across billions of years. And as you watch it turn, you realize something profound. Galaxies are not static. They are not rigid. They are not permanent. They are rivers of stars. They are evolving stories. They are time made visible. And you, drifting through them, are built from their ancient light. As you drift gently back toward the denser layers of the disk, imagine the Milky Way as a vast, shimmering clock, one whose gears move not in minutes or hours, but in millions and billions of years. Every region you pass holds its own tempo. Some places rush with the birth of massive stars. Others rest in long cycles of quiet accumulation. This slow, balanced rhythm gives the galaxy its heartbeat, a pulse so subtle that only by drifting through its layers can you feel its rise and fall. Near the midplane again, you find yourself surrounded by stars that move together in long, flowing streams. These aren't remnants of destroyed galaxies, but moving groups, clusters of stars that form together and drift through the disk as elongated families. Over time, their formation nebula dissipates, leaving only their shared motion to reveal their connection. Some famous groups, like the Hyades or the Pleiades, still hold tightly together. Others have stretched into extended waves, barely distinguishable from the general stellar population except by precise measurements. These moving groups help astronomers piece together the galaxy's past. By studying their age, motion, and composition, scientists reconstruct where they formed, how they migrated, and how the galaxy's gravitational structures nudged them into new orbits. They are like drifting pages torn from the same book, carried by a cosmic breeze, yet still telling part of the same story. You glide farther and notice how the interstellar medium becomes patchy, dense clouds beside wide, empty lanes. This patchwork is shaped by the balance between gravity pulling material inward and heating processes pushing it outward. Ultraviolet radiation from young stars carves cavities. Supernova shock waves open channels. Magnetic fields stretch clouds into filaments. The result is a fractal landscape, structures within structures within structures, each influencing the next scale down. As you pass through one dark cloud, you feel the temperature drop again. Here, shielded from starlight, chemical complexity thrives. Molecules like ammonia, formaldehyde, and methanol float within the cold gas. Dust grains accumulate icy mantles that form water, carbon dioxide, and organic compounds. These ices may later seed planets with the ingredients necessary for life. The galaxy is not merely forging stars. It is quietly preparing biochemical building blocks across thousands of light years. Deeper inside this cloud, you sense turbulence, slow, undulating waves of motion. Turbulence in the interstellar medium is unlike anything on Earth. It spans a vast range of scales, from hundreds of light years down to tiny eddies near dust grains. This turbulence shapes where stars will eventually form. If a region becomes dense enough, gravity overcomes the chaotic motions and collapse begins. If not, the cloud remains a cold reservoir, drifting until some future disturbance ignites its potential. Leaving the cloud behind, you approach a rare, striking region, a giant molecular complex stretching across hundreds of light years. These complexes are the galactic engines of star birth. Ophiuchus, Orion, Monoceros, Carina, each filled with bright nebulae and intricate clouds. You drift above such a region now, watching bright pillars of gas sculpted by radiation, curling like smoke in slow motion. Some of these pillars contain embedded protostars. Others represent the last remnants of clouds evaporating under intense ultraviolet light. Inside this region, massive stars form in clusters, their births violent and energetic. These stars will live only a few million years, short lives for such bright giants. They burn so intensely that they often disrupt the very clouds that formed them, triggering additional star formation at their peripheries. This cascading process, where one generation triggers another, is a hallmark of starburst regions. Further into the disk, you find regions shaped by interactions with spiral arms. When gas enters a spiral arm, it slows and compresses, forming dense ridges. As the gas exits the arm, it expands again. This compression forms regular patterns, lanes of star formation, clusters spaced like beads along filaments. These patterns can persist for tens of millions of years before dispersing. You drift past a lane of bright OB stars, immense, luminous, and near the ends of their lives. Their ultraviolet radiation illuminates nearby gas, turning it into glowing blue and pink nebulae. Eventually, some will explode in supernova events, ejecting shock waves that will shape the disk for thousands of light years. The heavy elements these stars produce, iron, nickel, silicon, will seed the galaxy, eventually becoming part of planets and living systems. Moving outward, you sense subtle corrugations in the disk, vertical ripples that arc above and below the midplane. These waves may be the result of past encounters with dwarf galaxies or dark matter substructures. They are faint but measurable, like ripples spreading across a pond long after a stone has fallen. Even after billions of years, the galaxy still remembers these encounters, storing their echoes in the motion of stars. In one such ripple, you find stars moving in a synchronized wave pattern, rising and falling as they orbit. This vertical motion is gentle, spanning thousands of light years, yet it shows how dynamic the disk truly is. Stars are not fixed. They bounce, oscillate, drift, migrate, and twist through the galaxy's architecture. You move beyond the ripple into a more tranquil stretch of the disk. Here, red dwarfs dominate the population. Faint, long-lived stars spread across every direction. Their collective light forms the soft background glow of the Milky Way when seen from dark places on Earth. These dim stars are quiet, stable, and nearly eternal. The majority of planets in the galaxy likely orbit stars like these. They are cosmic candles, burning for trillions of years, far outliving the massive stars whose brilliance shapes nebulae. As you drift on, you come upon an ancient open cluster. Its bright stars have mostly faded or died. Only smaller, redder stars remain. The cluster is dispersing slowly. Tidal forces nudge its members outward. Some have already escaped, blending into the disk. Others linger, bound by the last threads of gravity. Eventually, the cluster will dissolve completely, leaving behind only a chemical fingerprint, its stars sharing a distinct composition that reveals their shared origin. Farther still, you encounter a region dominated by old stellar populations, thick disk and halo stars migrating through the disk. These stars have lower metallicity, evidence that they formed before many of the galaxy's heavy elements existed. They orbit with higher velocity dispersions, their motions influenced by early mergers and chaotic formation processes. Some travel in elongated loops. Others plunge up and down through the disk. They form a stellar archaeology layer, preserving the galaxy's earliest chapters in their motion and composition. You rise slowly toward the halo again, feeling the transition as star density drops. Streams become more visible, thin lines tracing orbits of ancient mergers. Some streams wrap around the entire galaxy. Others form loops or fragmented arcs. Each one is a scar of past interactions, preserved across billions of years. One stream, dim and fragile, curves beneath you. Its stars are so sparse that from any single point within it, you would barely notice the stream existed. Yet taken together, they form a coherent structure, a whisper of a long-lost cluster or dwarf galaxy. Their orbits stretch like stretched fabric, thin, delicate, shimmering against the dark. Far in the distance, the halo blends into the cosmic background. Faint dwarf galaxies drift there, some barely held by the Milky Way's gravity. Others are only passing through. Beyond them lies the intergalactic medium, a vast, diffuse soup of ionized gas, dark matter filaments, and faint radiation. The Milky Way itself moves through this medium, orbiting the center of the local group and slowly falling toward Andromeda, the nearest giant galaxy. The two are on a collision course, though collision is not the right word. Their stars are so far apart that when the galaxies merge billions of years from now, few stars will actually collide. Instead, their shapes will distort, their orbits will tangle, and their supermassive black holes will spiral together. What emerges from that long process will be a new galaxy, larger, smoother, quieter. As you return your gaze to the disk below, you realize how connected everything is. The galaxy's evolution, its collisions, its gas flows, its star-forming cycles, will shape not only the Milky Way's future, but the structure of the galaxy that replaces it. And through all this slow, majestic change, one truth remains constant. Galaxies are not static places. They are cosmic memories, recording everything, forgetting nothing. And you, drifting through this great luminous river, carry inside you the atoms made by these ancient stories. As you drift along the outer rim of the thick disk, you begin to notice patterns that are subtler than spiral arms, yet grander than the movements of any individual star. These are the galactic cities, massive stellar agglomerations that contain thousands or even millions of stars moving in loose synchrony. They are not bound tightly like classic globular clusters, yet they remain distinct enough to be recognized as families. Some are remnants of ancient mergers, fused into the disk long ago. Others are born from giant molecular complexes that seeded star formation on enormous scales. They resemble cosmic neighborhoods, each with its own age, composition, and dynamic history. As you descend back toward the midplane, you begin to sense the galaxy's chemical gradient, the slow shift in metallicity from the rich inner regions to the sparse outer rim. Closer to the center, stars contain heavier elements forged in countless generations of supernovae. Out here, the stars are more primitive, their compositions echoing earlier cosmic epochs. This gradient is not accidental. It reflects billions of years of recycling, migration, and enrichment. Every star you pass whispers a bit of this chemical story. You drift through a region where compact planetary nebulae glow faintly in turquoise and violet shells. These are the remains of stars like the Sun, stars that lived long, stable lives before gently shedding their outer layers. These shells, expanding slowly across light years, carry enriched material back into the interstellar medium. Over millions of years, these atoms will be stirred, cooled, compressed, and incorporated into future generations of stars and planets. The galaxy breathes through these cycles, inhaling gas into stars and exhaling it back into space. A little farther ahead, you encounter remnants of more violent endings. Supernova remnants stretching in ghostly loops of red and purple. Unlike planetary nebulae, these are chaotic, tangled forms shaped by shock waves traveling thousands of kilometers per second. Some knots contain heavy metals forged in the final seconds of a star's life. Others are glowing shocks where ejected material slams into surrounding gas. These remnants seed the galaxy with the elements required for rocky planets, magnetic fields, and even biological chemistry. Without these violent deaths, the galaxy would remain chemically simple, unable to support complex forms. As you continue drifting, you sense how the galaxy blends old and new in every direction. A cluster of young blue stars sparkles nearby, surrounded by the dusty remnants of their natal cloud. Their brightness contrasts with the faint red glow of the thick disk stars passing above them, stars that may be 10 billion years old or more. The galaxy is not uniform. It is layered with different eras, different memories, and different rhythms of time. Passing beyond this region, you encounter a vast complex of interstellar bubbles overlapping like enormous translucent spheres. These bubbles formed where clusters of massive stars emitted strong winds and ultraviolet radiation, carving out cavities in the surrounding medium. The edges of these bubbles glow softly, and where they intersect, star formation ignites. This chain reaction of overlapping fronts is a key driver of the galaxy's evolution, each generation shaping the next, forging patterns that ripple outward across thousands of light years. Within one such bubble, you drift through a tunnel-like region where the gas flows outward in a gentle breeze. This is part of the galaxy's breathing, the slow circulation of hot material rising into the halo, cooling, and later falling back toward the disk. This cycling regulates temperature, redistributes heavy elements, and maintains the delicate balance required for new stars to form. The galaxy, vast as it is, relies on this subtle equilibrium to sustain its long-term structure. Moving on, you approach a region of the disk where gravitational waves have left their imprint, not in the form of detectable space-time distortions, but in the synchronized oscillations of stellar orbits. When massive mergers occurred elsewhere in the local group, faint ripples propagated across the galaxy, subtly influencing the motions of stars. These echoes are faint, nearly invisible, yet incredibly informative. By studying them, astronomers can deduce the timing of past collisions and even identify dark matter clumps that passed through long ago. You drift farther and feel the increasing influence of the central bar, a structure you cannot see directly from this distance, but whose gravitational signature stretches across the disk. It organizes the flow of gas, channeling material inward along elongated orbits. This inflow fuels star formation near the center and may even provide occasional feeding for the supermassive black hole. Though you remain far from the core, the bar's influence shapes the pattern of everything around you. The spacing of spiral arms, the distribution of molecular clouds, and even the long-term migration of stars. Within one such bubble, you drift through a tunnel-like region where the gas flows outward in a gentle breeze. This is part of the galaxy's breathing, the slow circulation of hot material rising into the halo, cooling, and later falling back toward the disk. This cycling regulates temperature, redistributes heavy elements, and maintains the delicate balance required for new stars to form. The galaxy, vast as it is, relies on this subtle equilibrium to sustain its long-term structure. Moving on, you approach a region of the disk where gravitational waves have left their imprint, not in the form of detectable space-time distortions, but in the synchronized oscillations of stellar orbits. When massive mergers occurred elsewhere in the local group, faint ripples propagated across the galaxy, subtly influencing the motions of stars. These echoes are faint, nearly invisible, yet incredibly informative. By studying them, astronomers can deduce the timing of past collisions and even identify dark matter clumps that passed through long ago. You drift farther and feel the increasing influence of the central bar, a structure you cannot see directly from this distance, but whose gravitational signature stretches across the disk. It organizes the flow of gas, channeling material inward along elongated orbits. This inflow fuels star formation near the center and may even provide occasional feeding for the supermassive black hole. Though you remain far from the core, the bar's influence shapes the pattern of everything around you. The spacing of spiral arms, the distribution of molecular clouds, and even the long-term migration of stars. As you drift over a dense lane of gas and dust, you find a stellar nursery hidden within. Here, protostars glow softly in infrared hues. Their disks swirl, flatten, and develop subtle rings where planets may one day form. Jets of material streak outward from the poles of some of these forming stars, narrow beams driven by magnetic fields and rotation. These jets carve channels through surrounding gas, shaping the local environment. Each forming star is not just a passive object. It is an active sculptor, influencing its neighborhood even before it shines. Moving beyond this region, you enter a quieter part of the disk where star formation is sparse. The stars here are older, more stable, and more uniform. Many follow circular orbits, maintaining the smooth rotational shape of the disk. Yet even here, subtle patterns emerge, streams of stars migrating outward or inward, shifted by spiral arm resonances or gravitational perturbations. These migratory flows help blur the chemical gradient of the galaxy, mixing older metal-poor stars with younger metal-rich ones over billions of years. You rise above the disk and see below you a patchwork of bright and dark regions, nebulae, clusters, clouds, and empty lanes forming a tapestry of motion and structure. The spiral arms appear less like rigid curves and more like braided pathways where star formation has flourished. Farther out, the arms fragment into segments that twist gently, influenced by density waves, stellar feedback, and dark matter clumps. As you drift outward along one such fragmented arm, you encounter a cluster of hot, massive stars nearing the ends of their lives. Their intense radiation sculpts the clouds around them, forming rimmed structures and shadowed alcoves. Some of these stars will go supernova soon, sending shock waves that compress distant pockets of gas. Others may collapse directly into black holes, vanishing quietly into the dark, but leaving behind gravitational imprints that subtly affect the motion of nearby stars. Beyond them, you find an enormous void-like region, an empty cavity where almost no stars reside. This is not an accident. It is the result of stellar feedback carving out a bubble so vast that it spans hundreds of light years. The gas here has been swept outward, leaving a hollow heart. Eventually, new gas may drift in, or the bubble may merge with another cavity, reshaping the local environment. Even emptiness has purpose here. As you travel onward, you approach the boundary between the thin and thick disk once more. Here, stars vary dramatically in age and metallicity. Some halo stars dive through the region on eccentric orbits. Others drift slowly, unaffected by the chaos around them. In this transition zone, the galaxy's layered history becomes most apparent, a blend of old, intermediate, and young populations coexisting in overlapping orbits. You drift along one of these halo star paths. The star moves in a graceful arc, its orbit tilting far above the disk before descending again. Its motion speaks of ancient events, perhaps a merger long forgotten or a gravitational encounter with a compact cluster. This star has wandered for billions of years, tracing a path through regions now unrecognizable from when it first formed. Finally, you rise gently back into the halo, where the galaxy grows quiet, dim, and expansive. Stellar streams are clearer here. Globular clusters shimmer like ancient lamps. The Milky Way's disk below glows as a soft, mottled ribbon. And scattered throughout this vast expanse are isolated red giants, stars nearing the ends of their long lives, shining like soft embers drifting in the cold. The halo is a place of memory, a region that records the galaxy's deepest past. Every star here is a clue to some earlier chapter, every orbit a fossil curve left by forgotten forces. And as you drift, you sense the scale of it all. A galaxy that breathes, remembers, evolves, and transforms across ages far beyond human reckoning. You are not just observing it. You are part of it, made from its light, its remnants, its stories. As you drift farther into the calm outskirts of the halo, the glow of the disk begins to fade behind you. The Milky Way stretches beneath your vision like a luminous ribbon, soft and textured, its spiral arms no longer sharp, but blurred into a quiet haze. Out here, the stars are sparse, the distances colossal, and the silence almost absolute. Yet, even in this isolation, the galaxy is full of motion, subtle tides, faint radiation, and long-traveling particles whispering through the void. In the darkness, a faint blue beacon blinks with steady precision. You approach it slowly, realizing it's a pulsar, a rotating neutron star sending beams of radiation into space like a cosmic lighthouse. Each pulse arrives with the accuracy of an atomic clock. These remnants of massive stars are some of the most stable timekeepers in the universe. Their steady rhythms help astronomers map gravitational waves, locate star clusters hidden by dust, and track the galaxy's slow, complex rotation. The pulsar hums softly as you drift past, its rhythmic flashes marking the passage of time on a scale far different from human clocks. Moving deeper into the halo, you encounter another subtle glow, a faint X-ray haze drifting around a collapsed binary system. One star within the pair siphons material from its companion, heating it to millions of degrees. This gas spirals inward, lighting up the surrounding region in high-energy light invisible to human eyes. Systems like these reveal the violent extremes hidden within the galaxy. Even from afar, you can sense the intense gravity shaping the dance of these two objects, pulling, consuming, transforming. A few thousand light years away, you notice something unusual, a narrow filament of stars stretching across the darkness like a delicate thread. This is a stellar stream, the remnants of a small galaxy or cluster torn apart by the Milky Way's tidal forces. Each star within it follows a similar orbit, forming a graceful arc that wraps gently around the halo. By studying these streams, astronomers can measure the unseen distribution of dark matter. Each twist and curve reveals something about the galaxy's invisible skeleton, mapping its hidden mass with quiet precision. Drifting along the path of this stream, you find that its stars differ subtly from those in the halo. Their chemical signatures show a common origin, a cluster that once lived tightly bound before being dismantled by gravity's slow hand. Now, these stars drift freely, stretched thin across the sky. Some shine with soft red hues, others with faint blue flickers. They are separated by vast distances, yet connected by a shared history, a cosmic family dispersed, but still following the same ancient path. Farther still, you sense the presence of the galaxy's hot halo, a diffuse cloud of gas enveloping the Milky Way in a vast sphere. This gas glows faintly in X-rays, warmed by supernova explosions and ancient collisions. Though thin beyond imagination, it contains more mass than all the visible stars in the disk. Its temperature reaches millions of degrees, yet its density is so low that you could drift through it without feeling a thing. This halo acts as the galaxy's reservoir, feeding gas inward over billions of years, replenishing what star formation consumes. As you descend closer to the disk once more, you pass through a region of faint microwave emission produced by spinning dust grains. These tiny particles, some no larger than smoke, rotate rapidly under the influence of magnetic fields, emitting soft light across wavelengths invisible to the eye. This faint glow reveals the galaxy's magnetic structure, which threads through the disk and halo like an unseen tapestry. These fields influence star formation, shape supernova remnants, and guide the flow of cosmic rays across vast distances. Below you, a dark lane slices across the glowing disk, a region rich in interstellar dust that absorbs visible light. Behind this veil lies one of the galaxy's most active star-forming complexes, hidden from view in optical wavelengths. As you shift your perspective, the infrared glow becomes visible, revealing sprawling nebulae filled with the soft pinks and oranges of hydrogen emission. Inside, newborn stars carve cavities with their radiation, shaping pillars, ridges, and luminous fronts. These structures evolve slowly, sculpted by winds and feedback from the massive stars within. At the edge of this region, you drift through a long filament of cold molecular gas. These filaments, stretching dozens of light years, serve as the scaffolding for star formation. Gravity pulls them into narrow threads, while turbulence and magnetic fields weave them into complex shapes. Over time, dense knots form within these filaments, collapsing into new stars. Some knots fragment into clusters, sowing future stellar families throughout the disk. These filaments are delicate bridges in the galaxy's architecture, quiet, dark, and essential. Deeper into the disk, you encounter an enormous molecular cloud, one of the galaxy's great dark giants. It stretches across hundreds of light years, its interior shielded from starlight. Within its coldest cores, temperatures approach just a few degrees above absolute zero. Here, molecules freeze onto dust grains, forming icy mantles rich in carbon and oxygen compounds. These frozen materials may become the seeds of future planets, comets, and possibly even the chemistry that leads to life. The galaxy's future is hidden in these cold, quiet cradles. Near the fringes of this cloud, you notice faint radio emission tracing hydrogen atoms in their simplest form. These radio waves, produced when hydrogen's electron flips its spin, provide astronomers with a powerful tool to map the galaxy structure. The warp of the disk, the flows of gas, and the hidden arms become visible through this spectral fingerprint. The hydrogen line acts like an interstellar beacon, revealing the galaxy's shape long before visible light telescopes could peer through the dust. As you rise once again toward the halo, you encounter a region where hot gas erupts upward through the disk, one of the galaxy's massive superbubbles. Formed by overlapping supernova from a cluster of massive stars, these bubbles punch through the plane like cosmic chimneys, feeding energy, metals, and magnetic fields into the halo. From above, these chimneys appear as faint columns extending far from the disk, slowly dispersing their contents into the surrounding medium. They help shape the galactic fountain, a cycle of ascent and descent that regulates the evolution of the interstellar medium. You drift toward one such column, feeling the faint warmth of gas heated to millions of degrees. Though invisible to the naked eye, this plume is filled with X-ray light, a reminder of the colossal forces at work within the Milky Way. These superbubbles expand over millions of years, merging, splitting, and reshaping the surrounding environment. They alter star formation by clearing pockets of gas while compressing others, making them both destroyers and creators of new possibility. Farther above the disk, you sense the faint pull of stellar streams left from ancient encounters. Some loops extend far into the halo, completing enormous orbits over billions of years. Others wrap tightly near the disk, twisted by its gravitational field. These streams form a network of subtle pathways, invisible to the eye but recorded meticulously by missions like Gaia. Each star within these streams carries a story of disruption, a memory of a galaxy long consumed or a cluster long dissolved. You drift along one such path, feeling the subtle differences in stellar motion. Unlike the circular paths of thin disk stars, these orbits wobble, tilt, and stretch. They reveal the lopsided nature of the galactic potential, influenced by unseen masses and past collisions. The Milky Way, though serene from afar, bears the scars of an active and tumultuous past. As your journey continues, the galaxy's soft glow shifts below you, and the black expanse of intergalactic space opens above. Yet even this dark emptiness is not truly void. Neutrinos, cosmic rays, and stray dust grains stream outward, carrying messages from the galaxy's heart. The Milky Way hums with radiation, some gentle, some fierce, all part of a cosmic symphony older than any civilization. And here, hovering between the disk and the vast beyond, you sense the galaxy's heartbeat. Slow, immense, continuous. It pulses not in minutes or hours, but in tens of millions of years. In star births, in spiral shifts, in the quiet rain of gas from the halo. You drift quietly in this boundless space, part of its story, part of its motion, part of its memory. As you move gently away from the high halo and descend once more toward the outskirts of the disk, the Milky Way slowly brightens under you. Its soft starlight ripples like a great ocean made of billions of suns. The spiral arms, faint yet unmistakable, arc outward in braided patterns, crossing and fading like cosmic brushstrokes. From this vantage point, the galaxy appears serene, but as you drift closer, the complexity hidden within its light becomes clear again. Flows, filaments, tides, and subtle migrations shaping the disk from within. You pass through a region where the disk begins to transition into its far-flung outer layers. Here, stars are sparse and gas is thin, yet the spiral structure still leaves its imprint. These are the outer arms, faint, stretched, and broken into segments by the waning influence of density waves. Though delicate, these arms contain clues about the galaxy's growth. Their fractured arcs hint at interactions with satellite galaxies, the influence of dark matter filaments, and the gentle pull of unseen structures that tug at the outer rim. You drift along one such segment, barely illuminated by a scattering of young blue stars. These stars stand out like cold embers in the dark, evidence of rare star formation far from the galactic core. Out here, the interstellar medium is so thin that new stars form only when gas is compressed by passing waves or distant gravitational nudges. The result is a fragile chain of stellar clusters, each one a small oasis of light in an otherwise quiet expanse. Farther inward, you sense the presence of an enormous gaseous arc sweeping across the galaxy's outer regions. This is a warp, an elegant bend in the disk that lifts its edges upward and downward like the gentle curl of a spinning ribbon. At this distance, the warp is pronounced, a vast vertical wave sculpted by tidal forces from satellite galaxies, such as the Magellanic Clouds. Their gravitational influence pulls at the Milky Way's outer layers, creating an undulating motion that migrates slowly around the disk. From within, the galaxy may appear steady, but from afar, it sways like a ship riding a cosmic tide. Following the curve of this warp, you drift through a domain filled with high-velocity clouds, massive pockets of gas plunging toward the disk at hundreds of kilometers per second. These clouds may originate from interactions with dwarf galaxies, from cooling fountain flows, or even from the cosmic web beyond. As they fall, they stir turbulence and seed fresh star-forming material into the outer disk. Their collisions with existing gas ignite waves of compression that ripple inward, acting as catalysts for new generations of stars. Descending closer to the disk, you enter a region dotted with isolated red giants, each burning brightly against the dark. These stars, swollen and aging, shed material into the interstellar medium, forming expanding shells of gas. Over time, their slow winds enrich the thin outer disk with carbon, nitrogen, and complex molecules. Though quieter than supernova explosions, these winds carry essential ingredients for the galaxy's chemical evolution. Every gentle outflow contributes to the subtle enrichment that allows planets and eventually life to form. Continuing inward, you encounter a long arc of ancient stars moving together in a graceful, looping orbit. This arc is a relic of a long-ago merger, an entire dwarf galaxy absorbed by the Milky Way billions of years earlier. Though its original structure is gone, its stars remain bound to one another, tracing a fossil orbit through space. Their chemical signatures are distinct, low in heavy elements, formed in an environment far simpler than the Milky Way's own. These stars drift like quiet messengers from a forgotten era, preserving in their light the memory of a smaller world devoured by a larger one. As you drift closer to the thin disk, the density of stars increases, and the darkness begins to glow with a pale silver haze. Here, the spiral arms become clearer. They aren't rigid lanes of stars, but shifting patterns, waves of density moving like slow-motion waves through an ocean of gas. In these regions, the gravitational forces gather material into arcs, lighting them with bursts of star formation. The arms are not structures you could touch. They are rhythms, moving patterns, ebbing and rising over millions of years. Along one arm, you approach a massive molecular cloud complex stretching across hundreds of light years. Its dark silhouette is pierced by the faint glow of embedded protostars warming the gas around them. Jets streak outward from some of these forming stars, funneling angular momentum into the surrounding medium. Shock waves ripple through the cloud, creating dense ridges where new stars will one day ignite. You sense the delicate balance of forces, turbulence trying to tear the cloud apart, gravity pulling it inward, magnetic fields threading through it like invisible scaffolding. These clouds are not uniform. They contain knots, filaments, and cold pockets sculpted by past generations of stars. Some areas have already collapsed into clusters, while others remain on the edge of collapse, waiting for a nudge from a passing wave or a shock front. Star formation is not a smooth process. It is a chaotic sequence of local triggers, feedback loops, and delicate equilibriums that unfold over immense spans of time. Leaving the cloud behind, you drift into a quieter stretch of the arm where older stars dominate. These are mid-aged suns, stable, yellow-white, with well-formed planetary systems. Many possess debris belts, asteroid fields, and icy outer reservoirs rich in organic compounds. Over billions of years, comets from these reservoirs scatter through their systems, delivering water and carbon-based molecules onto emerging planets. The ingredients for life may be transported in these icy messengers, seeded across the galaxy through countless impacts and migrations. A little farther ahead, you encounter a peculiar region where the spiral arm bends slightly, forming a localized kink. This distortion is subtle yet significant. It may indicate the presence of a small dark matter substructure, a clump of invisible mass that has perturbed the orbiting material. Although unseen, such clumps can shift the paths of stars, stretch gas streams, and even trigger local star formation. They reveal the unevenness of the galaxy's gravitational field, a reminder that the Milky Way structure is not carved from light alone. Drifting inward, you notice the gradual brightening of the disk as more stars gather around you. Their combined glow creates a warm, diffuse light that blankets the region in soft hues. Here, open clusters are more common, tight groups of young stars born from the same cloud. Some clusters remain bound for hundreds of millions of years, while others dissolve rapidly, contributing their stars to the galactic population. These clusters mark pockets of recent star formation, glowing briefly before dispersing into the broader disk. You glide past one such cluster. Its brightest members are hot O and B-type stars, luminous but short-lived. Their intense radiation sculpts the surrounding gas into arcs and cavities. Over time, these massive stars will go supernova, sending shock waves that may trigger new waves of star formation in distant regions. The cluster is temporary, but its influence endures, an ephemeral spark igniting patterns that ripple across light years. Moving downward through the disk, you encounter regions where the structure becomes lopsided. The density of stars is uneven, the gas thickness varies, and the arms appear slightly shifted. These asymmetries trace the galaxy's interactions with satellite galaxies and dark matter concentrations. Like tides on Earth, they pull and distort the disk, creating gentle yet persistent waves that propagate outward over millions of years. You continue drifting until the spiral arms begin to fade once more. The stars grow more sparse, the gas thinner, and the disk transitions toward the halo again. Here, the chemistry shifts. Older stars dominate, carrying compositions that echo the galaxy's youth. Some wander on inclined, elongated orbits, dipping in and out of the disk with each revolution. Their paths preserve ancient gravitational scars, remnants of encounters that have shaped the Milky Way's long evolution. Rising back into the halo, you feel the atmosphere of the galaxy thinning around you. Below, the disk glows softly, a sprawling sheet of starlight. Above, the expanse opens toward intergalactic darkness. Yet even here, you are not beyond the galaxy's reach. Stellar streams arc across your path. Globular clusters shimmer like old lanterns, and the hot halo breathes slowly, cycling material between the disk and the cosmic environment beyond. In this quiet space, the Milky Way feels vast, alive, and ancient. Its structures, arms, streams, filaments, and flares interlock in delicate harmony, revealing a galaxy shaped not by a single force, but by countless influences across billions of years. And as you float in this borderland, you sense again the truth running through all of it. Nothing in the galaxy is truly still. Everything drifts, merges, dissolves, or begins again. You, too, are part of that quiet motion. A small awareness drifting through a story far older than time can hold. As you descend once again toward the luminous surface of the galactic disk, you sense a subtle shift in texture, an increase in the density of starlight, a gentle brightening of the cosmic ocean stretching below. The Milky Way's vast structure reveals itself in overlapping layers, the mottled lanes of dust, the shimmering fields of older stars, and the sharp glints of newly formed suns scattered like diamonds across a velvet sheet. From this vantage point, the galaxy seems steady, but as you drift closer, the intricate dynamism returns in full force. You enter a region where the interstellar medium becomes thick with faint, curling tendrils of dust. These dust lanes, woven tightly through the spiral arms, twist and ripple like smoke suspended in slow motion. They are not obstacles to the galaxy's light. They are the architects of its future stars. Each grain of dust plays a role in cooling gas, shielding fragile molecules, and setting the stage for the earliest phases of gravitational collapse. In these lanes, chemistry flourishes. Carbon chains, simple sugars, alcohols, and aromatic hydrocarbons form, waiting silently for the day they may be delivered onto newborn planets. As you drift deeper into the dust-rich region, the light dims around you, muted into deep shades of copper and brown. Yet through the haze, you perceive soft infrared glows, protostars emerging gently from their cocoon-like shells. Some are just beginning to warm, their surrounding disks slowly flattening and gathering mass. Others shine brighter, their jets slicing through the darkness with narrow beams of ionized gas. These gentle eruptions mark the earliest breaths of new suns, voyaging into existence with a mix of chaos and grace. Passing beyond this cradle of forming stars, you approach a region bustling with stellar activity. Here, ultraviolet radiation from young, massive stars illuminates the surrounding gas, revealing vast, glowing nebulae. Enormous bubbles carved by high-energy winds overlap and merge, forming honeycomb structures filled with shimmering light. These bubbles can expand for dozens of light years, sculpting the interstellar landscape into ridges and cavities. The interplay between expansion, collapse, and radiation forms an endless cosmic feedback loop, one generation of stars clearing the way for the next. As you glide among these shining chambers of gas, you sense that the galaxy is not merely creating stars, it is shaping itself. Each burst of formation sets off a chain of quiet events, shock waves rippling outward, magnetic fields twisting and tightening, dust grains aligning with invisible currents. Over millions of years, these patterns echo through the disk, leaving behind a signature that astronomers can trace long after the clouds have dispersed. Farther inward, you approach a dense cluster brimming with life, stars so close together that their combined light washes through the region in waves. These clusters form in bursts, often containing hundreds or thousands of stars birthed from the same collapsing cloud. Some remain bound for long periods, held together by mutual gravity. Others drift apart quickly, their members scattering into the field like glowing seeds carried on a cosmic wind. Even after dispersal, their shared chemical fingerprints remain, allowing scientists to identify stars that were once siblings. You drift through one such cluster, sensing the distinct rhythm of its stellar population. At the center, massive stars burn blue and hot, blazing like cosmic torches. At the outskirts, smaller red dwarfs flicker quietly, their steady glow promising lifetimes far longer than the galaxy's spiral arms themselves. These stars will still shine when every bright giant nearby has collapsed, reminding the galaxy that longevity often comes in humbler forms. Moving past the cluster, you enter a region where spiral arms overlap, creating a compressed zone rich with gas and turbulence. These intersections are powerful engines of star formation. Here, the density waves that define the arms intersect with gravitational perturbations from past mergers, producing pockets of intense activity. In some cases, entire starburst regions ignite, vast swathes of space blooming with thousands of new suns over just a few million years. These regions act like cosmic festivals of light, brief but transformative, leaving behind clusters, associations, and remnants that echo through the galaxy long after the fireworks fade. As you drift onward, the starlight grows softer, transitioning into the older, more uniform glow of the galaxy's inner regions. Here, the stars are thicker, packed in intricate orbits that blend into a shimmering gold haze. Many are ancient, their compositions bearing unmistakable traces of the galaxy's earliest epochs. Some were born when the Milky Way was still assembling, an uneven cloud of gas just beginning to coalesce. Their motion through the disk is slow, deliberate, and often inclined, tracing paths shaped by gravitational interactions long forgotten. Above this luminous plane, subtle waves pass through the disk, ripples generated by distant encounters with passing dwarfs, dark matter clumps, and even the motion of the spiral arms themselves. These oscillations are incredibly faint, yet extend for thousands of light years. They behave like the residual vibrations of a colossal gong struck millions of years in the past. The Milky Way remembers every encounter, every collision, every distortion. The evidence lingers in its motions, its structures, its hidden folds. Continuing your journey, you rise again toward the slightly thicker layer of the galaxy known as the thick disk. This region sits above the thin disk and contains stars older, more metal-poor, and moving in more elliptical orbits. Many of these stars may have formed before the spiral arms fully settled. Their presence suggests ancient turbulence, the chaotic early days when the Milky Way grew not through orderly rotation, but through violent mergers and collapsing gas clouds. To drift through this region is to move backward in time, touching the echoes of an era nearly lost to cosmic memory. Beyond the thick disk, the galaxy begins to fade once again into the halo. The stars thin out, the glow softens, the expanse opens. Far below, the spiral arms shimmer like ghostly rivers of light. Far above, the darkness grows colder, vaster, quieter. Yet even here, the Milky Way continues to shape itself. Filaments of gas rise from the disk, cooling slowly as they ascend. Some will fall back, forming fountains that regulate the galactic ecosystem. Others may remain suspended in the halo for eons, waiting for a gravitational nudge to send them drifting inward once more. From this liminal space, you see the galaxy for what it truly is, not a static object, but a living, breathing structure. Its arms pulse with activity. Its halo whispers of ancient collisions. Its disk sways in gentle waves. And deep within its core, hidden by dust and time, a supermassive black hole anchors the entire structure with silent authority. The galaxy is not merely a place. It is an ongoing story, an unfinished cosmic symphony. And you, drifting in its quiet embrace, are part of that story. If your eyes feel heavy now, let them gently close. You've traveled through spiral arms, woven through nebulae. Listen to the quiet heartbeat of stars older than memory. And all the while, the Milky Way continued its slow, ancient turning beneath you. Tonight, as you settle into rest, remember that you are part of this galaxy, made from its dust, shaped by its light, connected to its long and luminous history. The same atoms that burn in distant suns move quietly through your body. The same elements forged in ancient explosions give strength to your bones and breath to your lungs. You are not separate from the cosmos. You are woven into it. So let your mind drift now. Let the starlight fade softly behind your thoughts. Let the quiet of the galaxy wrap around you like a warm, gentle tide. The journey will be here again whenever you need it. For now, sleep deeply. Dream softly. Good night.